So today we're going to do the last part of this unit. We're going to stay in chapter 9 in the Larson book. I think he tries to do too much in one chapter, honestly. I think he should have broken it into two chapters, but he didn't call me, so he didn't get my advice on that. Um, so anyway, this is going to end that. Now we're going to continue on with some other stuff before we take the test, just because of how we can't test on a Friday because the Fridays are too short, and I don't believe in tests on Monday in math because, well, that's evil. And so we're somewhat limited as to when we can test. And Wednesdays are a little short, and I'm like, okay, that leaves us Tuesdays and Thursdays. So anyway, um, we will tomorrow start the next unit. On Friday, you have a quiz on sections 9.4 and 9.5, which is comparison of series, and then absolute and conditional convergence. Okay, those things. But today we're going to learn the ratio and root tests. These tests are very similar. The ratio test gets used a lot. The root test, I'm going to show it to you. Occasionally it's helpful, but I don't think the root test is even required on the AP exam anymore. But I think it's something that it's like, it works the same way as the ratio test. Why not do it at the same time? All right, so the ratio test, like I said, this one gets used a lot. So if we have the summation of a sub n and it's a series of non-zero terms, notice here it doesn't have to be all positive, right? This chapter is kind of broken. This part of this unit is in two parts. The parts where everything had to be positive, then we looked at alternating series, then we looked at, well, what if some terms are positive and others are negative? Here, we need a series of non-zero terms. So the summation of a sub n converges absolutely if the limit as n goes to infinity of a sub n plus 1 over a sub n in absolute value is less than 1. And then diverges if the limit as n goes to infinity of a sub n plus 1 over a sub n is greater than 1. If, on the other hand, the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1, the test is inconclusive. It doesn't tell you anything. So we're seeing, just this ratio. So I need the terms to be getting smaller. That's why this can't be greater than 1, because if a sub n plus 1 over a sub n gets bigger than 1, that means that the terms have got to be getting bigger. Here, my terms need to be getting smaller. And they need to be getting smaller fast enough to where there's a real difference between them. Right? If you have, x plus 3 over x plus 4, well, yeah, x plus 4 is bigger, but as x goes to infinity, there's really no difference, right? They need to not grow at the same kind of a rate. So this test is used a bunch when you have factorials. In fact, anytime I have a factorial, my first impulse is going to use the ratio test on this. And the reason why is because if you have n plus 1 factorial, which you will because you're going to replace the n with n plus 1, that's equal to n plus 1 times n factorial, which is going to let you cancel some things out. So let's determine the convergence or divergence of each of these series. So here we have the summation as n goes to infinity of 2 to the nth over n factorial. Again, we should always first kind of look at, all right, does this pass the nth term test for divergence? As n goes to infinity, as we looked at, I believe it was yesterday, that factorials get big faster than even exponential functions do. So this is going to go to 0 as n goes to infinity. So you're like, great, It got past the nth term test. It's not obviously divergent, but we will do the ratio test on this. So we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1. So every n gets replaced with n plus 1. So 2 to the n plus 1 over n plus 1 factorial over 2 to the nth times n factorial, which is going to be equal to the limit as n goes to infinity of the absolute value 2 to the n plus 1 divided by 2 to the nth is going to be what? Two to the 18th divided by 2 to the 17th is what? 2.
Oh, so yeah.
And it's always going to be 2. Over n plus 1 factorial is n plus 1 times n factorial, right? When we divide that by n factorial, we end up with n plus 1. As n goes to infinity, that goes to 0, which is less than 1. So this test is a little bit different than some of the other ones, and that's the thing that also gets difficult. A lot of these are going to turn out to be 0, but not all of them. Some of them are going to turn out to be 2/3, right? Because so many turn out to be 0, people start to think, oh, it's got to be 0. No, it doesn't have to be 0. It just has to be less than 1. Therefore, this series converges. Absolutely. Now, I really didn't have to worry about the absolutely because it was all positive terms anyway. But if it had had some negative terms in it, I could still say that this converged absolutely. All right, so for this next one, it's a little bit more involved. First of all, the nth term test, it's hard to apply because n to the nth, so my base is growing and my exponent is growing. Is that faster than a factorial? We've never really talked about it. I don't know. Okay, so let's leave that for now. Let's go ahead and do the test. This is all positive terms, so I can go the limit as n goes to infinity of the absolute value of n plus 1 raised to the n plus 1 over n plus 1 factorial all over n to the nth over n factorial. So I'm going to take the limit as n goes to infinity. Not nearly as much cancels this time. I'm going to have n plus 1 raised to the n plus 1 over the n to the nth. There's nothing I can really do with those yet. I'll show you that we can do something with them in just a moment. And the n plus 1 factorial divided by n factorial, remember this is n plus 1 times n factorial, so it just leaves me with an n plus 1. I still need the absolute values on these. In the end, I can go, well, n's always positive. Everything's in here is positive. I can drop them. It's a good idea to just start keeping them from now because in the next unit, we're going to use them for something else. And if you drop them too soon, it causes major problems. Okay? It doesn't hurt you to carry the absolute value along here. Notice n plus 1 to the n plus 1 divided by n plus 1. You're like, okay. That would be like 5 to the 5th divided by 5, right? What is that going to be?
5 to the 4.
Right. So it's still n plus 1. The base didn't change. But the power now, instead of being n plus 1, is just going to be n when I divide over n to the nth. Well, I can write that as a single power. That'll be the limit as n goes to infinity of the absolute value of n plus 1 over n to the nth. And you might not recognize this, but I'm hoping you're going to recognize it when I write it in a different form. 1 plus 1 over n to the nth power. Do you remember us doing that one? We did it as an example. It showed up on a couple of homework problems. We can go through the whole deal if you don't, but do you remember what this went to? It is. It's exactly e. In fact, some books say that's the definition of e. It's the limit as n goes to infinity of 1 plus 1 over n raised to the nth power. And that's greater than 1. Therefore, this series diverges. So there's a pretty good amount of algebraic manipulation in these. This is why one of my colleagues and I used to say that, you know, if you wanted to be good at BC, you had to be an algebra animal. You had to be good at algebra. You had to be good at manipulating things symbolically. All right, let's take a look at this one and see what we can do with it. So you look at this and you're like, if I just had the 2 to the n plus 1 over 3 to the n, yeah, that would look sort of like a geometric. But then I've got this times n squared. I'm all very confused by this. Like, okay, well, let's see if we can do something with it. Okay, so we'll take the limit as n goes to infinity of the absolute value of n plus 1 squared. Now this will be 2. When I replace the n with n plus 1, this will be 2 raised to the n plus 2 over 3 to the n plus 1 over n squared 2 to the n plus 1 over 3 to the nth. So that'll be the limit as n goes to infinity. The n plus 1 squared over divided by the n squared, I'm not going to do anything with that just yet. I've got 2 to the n plus 2 divided by 2 to the n plus 1. What is that going to be?
2 to the n plus 1.
Nope. Pick a number for n. I don't care what it is.
3.
So that would be 2 to the 5th over 2 to the 4th. What is it? It's just 2. Remember, we subtract the exponents. N plus 2 minus n plus 1 is just 1. And we've got a 3 to the n plus 1 divided by 3 to the n, which is 3. All right, then as n goes to infinity, n plus 1 squared over n squared is going to go to what?
1.
1. So this is equal to 2/3, which is less than 1, and therefore this series converges absolutely. The root test is used way less often, and the setup is pretty similar. You have some series. Again, it needs to be non-zeros. The series is going to converge absolutely if the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1, diverges if that limit is greater than 1, and it's inconclusive if that limit, is equal to 1. This is best used when your terms involve an nth power, and it's not necessarily on the AP exam. So let's take a look at this one. Determine the convergence or divergence of this. We could use the ratio test on this, by the way, and it actually wouldn't be all that bad. But it's a little bit faster to use the root test. So I'm going to take the limit as n goes to infinity of the nth root of the absolute value of e to the, when I replace n with n plus 1, that's going to be 2n plus 2 over n plus 1 to the n plus 1 all over e to the 2n Oh, sorry. I was my fault. I was thinking that I said you could do the ratio test, and I started doing the ratio test in the middle of this. Terribly sorry. Don't need to do any of that junk. That's what I get for talking about one thing while I was doing something else. So we're going to take the nth root of e to the 2n over n to the n, which will be the limit as n goes to infinity of the nth root of e to the 2n is e squared. And the nth root of n to the n is n. As n goes to infinity, that goes to 0, which is less than 1, and therefore the series converges absolutely. So one of our goals in all of this is getting you to the place where you can actually look at a series and quickly identify what test could you use, but more than that, also be able to look at it and go, yeah, I've looked at this and I'm pretty sure this is going to converge, or I'm pretty sure this is going to diverge, just by giving it a quick inspection. So let's look at some examples. For each series, discuss the tests to use and the probable outcome, if possible. Okay? So for this one, for example, what test would you use? Yeah, nth term test. And I think you can do this in your head. Is this going to converge or is this going to diverge? It's going to diverge, because the limit as n goes to infinity of a sub n is not 0. All right, what about number 2? Yeah, it's a geometric. And pi over 6, well, it's, a little more than a half. So what is this going to do? This is going to converge. What about number 3? Yeah, you could do the integral test. Because it's relatively easy to take the antiderivative of this. All right, you just either do the integration by substitution or just undoing the chain rule. It seems to me that this one's probably going to converge. And you're like, well, what are you basing that on? Well, I've got e to the n squared is going to be in the denominator. So I've got n over e to the n squared. So I have a number over something that's getting big really incredibly fast. This is going to get small very quickly. Again, I'd like you to get to the place where you can kind of, you can walk up to it and you're like, okay, I'm pretty sure I know what's going to happen to this. All right, what about number 4? What kind of a test might you use for this?
Limit comparison.
Yeah, I'd probably use limit comparison. I'm going to compare it to 1 over n, which diverges. I think these are going to behave the same way. So I think this diverges. What about this one, for number 5?
Alternating series.
Yeah, alternating series test. That's likely to converge. But since that has some negative terms in it, do you think it's going to converge conditionally or absolutely?
Conditional.
It's conditional because without the alternating part, it's going to act a lot like the previous one, right?
Should you always put whether it's conditional or absolute?
If the problem doesn't ask, don't. But a lot of times they do. All right. What about this one?
Ratio.
Yep, ratio test. And when we divide it out, we're going to have an n plus 1 factorial divided by an n factorial, which is going to leave you with an n plus 1 in the numerator. This is likely to diverge. Also, we talked about the fact that factorials grow faster than exponentials. It's difficult to if they really are saying, show all of your work using the nth term test on this. I know that factorials are going to get bigger, but I would have to explain why I know that. All right? But this fails the nth term test, so it diverges. And then this last one, since everything's raised to the nth power, I'm going to use the root test. And I believe that this one is going to, if I took the nth root of that and then took the limit as n goes to infinity, I'm going to get a half which is less than 1, I believe that this is going to converge absolutely. And then I just put a note. It's things that mostly that I've said. Telescoping series are kind of rare, at least on the AP exam. You just don't see them very often. The root test is not on the AP exam at all. And the thinking behind direct comparison is an important idea. I almost never use it because I can use the limit comparison test just as easily in most cases. All right, so that's just kind of a wrap up of series that are made of constants. What we'll do in the next unit is we'll transition to series that instead of being made of constants have a variable in them and how that works. And a lot of this stuff is going to be applied to those as well. Particularly the ratio test, we'll apply that a lot, but we'll also we'll also be able to have to use geometric series tests and p-series tests and comparison tests, limit comparison, all those kinds of things as well. Okay? All right.